So just an overview of what we're going to go over. I'm just going to do kind of an introduction to multivariate analysis, and then we're going to talk mostly about principal components analysis today. All right, so why do we do multivariate analysis? Our world is actually multivariate. We have lots of multifactorial problems, lots of central sensors to measure things. And when you have all this working together, they need multivariate analysis to understand how things are working together to make predictions. We typically look at things in univariately in the process. So if you follow some control charts that you might normally see, you've got your limits around temperature and pH, but these things actually work together, and sometimes if you plot them against each other, you'll find that there are outliers that don't show up in the univariate world, but they do when you put multivariate limits on. We also have times when you can't measure things directly, like the temperature in a furnace. You can't put a thermometer in there as it will burst. So what we do is we take a measure with infrared emission spectrometry and convert and calculate what the temperature is based on that. And to do this, we often need a multivariate analysis approach. So in science, we aim to observe processes with available instrumentation or measurement techniques, and these follow laws of physics, and theoretical models can be modeled from first principles. Other processes are complex, and so then you need complex data analysis. So we use multivariate methods in order to analyze this data to get the right interpretation, to understand the background knowledge and theory, and for a comprehensive validation. So data analysis in practice, 40% is going to be what you bring to the table, your application knowledge and your common sense. That's 70% of what we're going to do. What we do with the unscrambler is we take care of the statistics and the mathematics for you, so you don't have to worry about that, and you can focus on your application and the interpretation of the data. So a couple of definitions that are important going into multivariate analysis is variance. Variance is the measure of the spread of your variable values. So each individual value, subtract the mean, square those, that's going to give you your variance. Your covariance is your measure of how two variables change together. So when one has a high value, does the other one have a high value all the time? If it has a low value, it has a low value in the Y. And then we also have correlation. And so that basically compares these linear dependencies. It's unitless, so it's just your covariance divided by the product of the standard deviations, where the standard deviation is the square root of the variance. One thing you need to be careful about with causality versus correlation. Be careful when you're interpreting your data. They've done surveys in Danish rural towns that show correlation of 0.75 between the number of babies born and the number of storks found in the area. But no one will argue with you anymore that storks bring babies. So you have to make sure that your interpretation makes sense with your application. We use multivariate analysis to discover hidden data structures. When we have data, we have observations. Those observations are composed of your data structure and your noise. Now, this is important to remember that it depends on your application what is considered the data structure and what is considered noise. If we take a matrix of components A, B, and C, depending on what we're trying to measure will determine what we say is the data structure. If we're trying to measure the concentration of A, then A is your data structure, and then the components that describe B and C are your noise. But if you're looking at C, then C becomes your data structure, and A and B become your noise. So there's lots of different multivariate analysis methods to choose from. It's going to depend on the type of answer you're looking for. We have data description, exploratory of data structuring and modeling. This is unsupervised typically. You're just looking at your data, you're characterizing your structure, and it's a qualitative analysis. PCA is a good example of this. You can also do discrimination and classification. So you're looking at trying to separate groups of data, quantitatively separating them. This can be either supervised, where you already know what your groups are and you're trying to figure out which things are in which groups, or it can be unsupervised, where you don't know what the groups are and you're trying to discover that. Some examples of this will be hierarchical clustering, SIMCA, and support vector machines. There's also regression and prediction. These types of methods relate sets of variables to each other. These are your indirect observations, like measuring temperature using NIR. These are going to be principal components regression, partial least squared regression, and multiple least squared. And again, today we're going to focus on this exploratory data structure and specifically principal components analysis. So the use of principal components analysis, as I said, is exploratory data analysis. You're using it to extract information and find out where your noise is so that you can remove that noise, and also to reduce dimensionality. Having trouble here. All right. So what we have is you have your X block of data. That is your data that you bring in. And as I said before, you've got your model, which is your structure, and your error, which is your noise. And you have to determine what that is based on your application. So in the principles of projection, each variable is defined as an axis. The coordinate system can be made up using all the variables, and this is called the variable space. This is just, an XYZ if you have 3 variables. And each object in a row is a sample, is a particular data point in the variable space. So your whole data table is a swarm of points in this variable space. And what we want to do is find out more about the structure of this swarm of data points. In many cases, the swarm of points has a specific shape in some direction, and this is going to be your PC1. You find the direction that has the most amount of variance in your data, and that is defined as the principal component 1. Once you've done that, then you find the next direction that is orthogonal or perpendicular to that space, PC1, and find the next direction of the most variability, and that's going to be your principal component 2. When we have the 2 principal components, we've now got a plane that we can project our swarm onto. So this is a window. It's a new way of looking at your data. And the process can be going on to find more principal components if you need to. Now, the maximum number of PCs that you'll have is either the minimum of the number of variables, so you cannot have more PCs than there are variables, or the number of samples minus 1. So if you have 30 samples and 400 variables, you can have no more than 30 principal components. If you have 3,000 samples and 40 variables, you're going to have no more than 40 PCs. We rarely get to this point, though. You want to use as few PCs as possible to understand your data. So now that we've defined our PC1 and PC2, we redraw the plot by projecting the points into that PC space. So the x-axis is defined along PC1, the y-axis is defined along PC2, and then where those data points fall in that space is called a score, which is just how far along PC1 is this data point. That's the score for that particular data on PC1. So as I said, what is a score? It is the distance from the mean along the PC that that data point is. And each point is a sample. A loading is going to be how much each individual variable contributes to that principal components. So the first pre-processing step that you do in pretty much any principal components analysis is mean centering. And you do this because what will happen is you'll find that your first principal component is just the mean of the data. So by mean centering, you eliminate that and center the data around the origin. It just makes analysis a little bit easier. Some other things that you might have to do is standardization, some variable scaling. If you have variables that are not on the same scale, this is just a box plot showing the median and quartiles of data. If you did an analysis on this, variable number 3 would pretty much define everything because it's so much higher than the rest of them. So if we center the data, it just subtracts the mean. And then you divide by the standard deviation of each individual variable, and now they're on the same scale so that you're not biasing your data by large numbers. So I'm going to do a quick example. So what I have here is some data that is from McDonald's, and it's nutritional data. And so we've got a number of different burgers, sandwiches, French fries, and desserts. And then our variables here, we have the calories, protein percent, carbohydrates, fat, and saturated fat. Now what I'm going to do is I'm going to right-click and insert a new column so that I can label this as type of data. And then I also need to right-click, change my data type to text, and I'm going to call all of these burgers. Fries. And again, if you highlight a group of cells that you want to say the same thing, you can right-click and do fill, and it allows you to type in here, and it will automatically fill that in. Now I'm going to change this data one more time to a category. This will help it be easier to visualize some of the information. So when I get a data set like this, I also want to define some ranges. You can do this to pull out individual columns. So I'm going to say type, and then I want to click all of these, and this is going to be my nutrition. And you'll see I have column sets over here, and you can look at just those individual columns. Not such a big deal in a small data set like this, but if you have a large data set, especially with spectral data, you sometimes only want to look at certain bands, and this is an easy way to pull those out so you don't have to redefine it every time you're doing analysis. So under tasks, I'm going to go to Analyze and Descriptive Statistics. I'm going to do this on the nutrition. And this is going to show me our box plots that shows our medians and the quartiles and the full range of the data. And what you can see from here is that we are on very different scales, so we are going to want to normalize the data before we do any analysis. So under Tasks, we can do Analyze, Principal Components Analysis, and we want to look at Nutrition, All. Always make sure that you mean center your data, unless you have a very good reason not to. We have a tab here that is Weights. So we want to select All and weight this by 1 over the standard deviation. That's just going to get that on the same scale. And you want to make sure to click Update, and you'll see the weights are added in here. We have a very small data set, so we're just going to do a full cross-validation method, but there are other options. You can do random, you can have custom, systematic if you have batches you want to pull out, systematic if you have repeated variables or repeated samples that you want to test, or by category variables. But we're just going to do full. And again, that's under this validation. So these are the plots that come up when you run a PCA analysis. One of the first things I look at is the loadings. And we can put show labels on here, and you can see what these variables are. So when you're interpreting your principal components loadings plot, we have this correlation loadings here. And what that does is everything outside of this ellipse is contributing at least 50% to that principal component. So principal component is going to be on the x-axis, so we're going to look which variables are falling within this range for those. And so here we're seeing that principal component 1 is mostly due to fat percent and the energy, so your calories. So that's the most variable. That's the variable with the most variations are going to be the energy and the fat. And we also have a little bit proteins contributing a little bit here. And then in PC2, we see it's going to be mostly carbohydrates that you're looking at. You also want to look at your explained variance. Your blue line here is your calibration explained variance. By definition, each PC will include more variability of the variance than the one before, but sometimes in the prediction, you'll have less. And sometimes here you have this negative. That just means that PC1 is definitely not enough to describe your data, so you cannot predict based on this. Sometimes this is an indication of an outlier. It's not in this case, but it does tell you, hey, I might want to look at my data a little bit more. So now let's look in your scores plot. We'll put our labels on. And you can see we've got a bunch of your Big Macs, your quarter pounders are down here. And if you look in this area on the correlation loadings, it's protein. So this is going to be your samples that have higher protein. Up here, we've got the French fries and apple pie, high on carbohydrates. That makes sense. So one thing we do want to look at, if you right-click in here, we can do sample grouping. And we can group based on type. If we create row sets, it creates labels based on the category values that we put on earlier. And we pull them all over here. And I'm just going to keep my label here as a name so that it keeps the original sample name. You might want to label it as your group. So if I did group, it would label as burgers, desserts, and fries. But we're going to go with name. And as you see, very clearly, all your burgers lumped together and your desserts wind up together, except for this apple pie. Now that's kind of interesting. So you've got your apple pie way over here away from the other desserts, but it's near the French fries. This is because the apple pie at McDonald's happens to be fried. So that actually does make sense, even though you might have expected the apple pie to show up more down with the other desserts. And when you look here under the PC1 and PC2, you see a percentage. That tells you how much of the total variability is described by that PC. So we've got 42% plus 34%, so that's 76% of the data is described by those two. We can take a look at PC3, and what's there is mostly saturated fat. So things high on the score in the Y direction now are going to be higher in saturated fats than those in the lower part. And as you see, your grilled chicken and just your regular hamburgers are lower on the saturated fat, and things like your quarter pounder, which has a lot of meat in it, is going to be higher in your saturated fat. So another thing you want to look at is your influence plot, and this is going to be your data points. So we've got the Hotelling t-squared, which is a measure of how far from the center of your model the data is. So how well is it described? Is it in that model space? And on your y-axis, you have your residuals. And what this is the amount of information that is left over after you have predicted, recalculated the data back into the original space. And so these are pretty good. These are low numbers. This line here is a 95% confidence line. So anything below here is within the model, and anything above might be out and have a high leverage on your model. You can change that if you want to be more strict or less strict, but they all fall very well within that space. In the scores plot, you also can make a Hotelling t-squared ellipse, and you see all of the data falls within the model space. Again, you can change those values depending on how precise you need your data to be, your analysis to be. It seems I have a question. In many of our data sets, we have category variables that we want to include in the modeling, both in PC and PLS, but we don't know how to include them. The only possibility we see is the coloring after modeling. Is it possible to use category variables so that they impact the modeling result? That is a good question, George. I am unsure at this particular moment, but I will get back to you on that one and follow up with everyone once I have discovered that. All right. So, as I said, you have to interpret your PCA model. This is where your knowledge of your data comes in. We've done the math for you, but now you have to understand what's going on. So one of the first things you need to think about is how many components do you actually want to take into account? The number of components in the model characterizes the structure of the data. The fewer PCs needed, the simpler the model, and it's typically easier to interpret. You want to look at the scores. That shows you how the data is distributed. You will see sample patterns, groupings, and similarities and differences can be studied. The loadings plot is used to understand the correlations between the variables, so which variables are actually important. Sometimes you might not need all of your variables, and from that loadings plot you can decide, oh, saturated fat didn't tell us anything really, so we can throw that out and we don't need to use that information anymore. And then your biplot will explain your samples in the score plot. So basically a biplot just puts the scores and loadings on top of each other. I'll show you that real quick if my computer wants to comply. I've gotten a number of questions if the slide and presentation will be available after after we're done. Yes, I am recording it and we will put this up online. So if we right click in here under PCA, scores and loadings, we can do biplot, labels. And what that does is now it shows your Y variables and your samples in the same space so that you can interpret a little bit more clearly that protein, quarter pounders, the sandwiches tend to have a lot of protein. French fries, apple pie has a lot of carbohydrates. So the first thing, how do you determine how many components you want to use? It's really going to depend on your application. What you want to look at, your criteria, is look at your explained variance or your residual variance. Those are the curves that I showed you, and you'll see if you have residual variance is how much is not explained. And the calibration variance, this will always trend towards 0. But your validation variance should begin trending towards 0, and at some point it will diverge. Once you start to diverge from this calibration variance, you're starting to model noise, so you want to stop. And where you stop on here really depends on how accurate you need to be. There's often a clear global minimum or maximum if you're looking at the explained variance. And so you tend to want to choose your first local minimum. And if it starts to plateau, that's when you want to stop, because then as you're adding individual components, it's not adding any extra data, information really. If you have outliers, it can disturb the normal behavior of these measures. You'll see that the model increases. There'll be a decrease in the PC2, and then PC3, it'll come back up again. So that's just something to notice and think maybe something's going on here. So you want to keep adding components as long as they carry structured information. You should always be able to interpret what your principal components means. And validation is the key to interpretation. So if here we have our model with one PC, we've got 50% of our data is explained and 50% is not explained. As we add another one, now we're up to 75% of the model is explained and 25% is not explained. In this case, at 3 PCs, you've modeled 90% and only 10% is not explained. Typical applications, you don't need to get much higher than 90%, depending on what you're looking at. If you're looking at sensory data, where in the food and beverage industry, for example, you might be happy stopping at 50% because people are much more variable than analytical techniques. So you want to look at the scores plot, and like I said, it shows how well the data is distributed. You can see sample patterns and groupings. In this particular data set, we're looking at 4 types of peas that are collected at 5 different times of harvest, and they're described by some sensory analysis, sweetness and mealiness, green color, and what we see is a trend with time. So earlier, the peas tend to be less sweet, and they become more and more sweet as you get later in the harvest. So you might find something like a time gradient. So your X loading plot is useful for understanding the correlations between variables and interpret the sample groupings. When you see variables that are very close together, that means they are highly correlated. So they tend to change in the same way. When they're directly across from each other, they tend to be anti-correlated. So as something becomes more sweet and more fruity, it tends to be less hard and less mealy. In your correlations loading plot, it shows the correlation between the variables and the PC. In this case, none of the variables are contributing to PC3 more than 50%, so PC3 is low importance to the model. So you would probably stop at PC2 in this particular case. So I'd like to show you another example using spectroscopic data. So what I have here is some near-infrared spectra of different fuels, and we know what their octane is. We've got some category variables for whether it's low octane, medium octane, high octane, and then there's also additives in some of these. So I'm just going to go to Task, Analyze Descriptive Statistics. We're going to look at our NIR spectra. Now in this case, you're looking for any variation. Here it looks like things are changing a lot. There's some outliers because there's some that are very high above the median of the spectra. But it looks like, for the most part, it's very stable. Now, for spectroscopic data, we almost never scale because the variability is important. So I'm going to do task principal components analysis, near IR spectra. I'm just going to look at my training set. We're not going to do any weighting because it's all spectroscopic data. It's all on the same scale. And here we can set up our validation. I'm going to say 10 segments. And it will automatically update. You can determine how many samples you want in a segment. You can say how many segments you want, and that they'll automatically update. But about 10% of your data is a good number. Let me say OK. And we put our hoteling T-squared on here. And right away, you can see there are two data points that are very different than the rest of them. If we go to sample grouping, we can define based on additive. Okay. Create row sets. And what we see here is that these two had the additive in them as opposed to the other ones. And when you look in the influence plot, you also see here. So you've got two different types of outliers here. You've got a outlier that is within the model. It has a high leverage. So it does fall within the model, but it's very different from the other calibration data points. And then you have one that is not described well at all. So the residuals is very high. If we want, we can go back and plot the spectra just to look at them. I forgot to do that first. It's always good to look at your data to see if you can see anything that stands out. And as you can see, you have some here that are very different than the rest. And if we do sample grouping in here, we can also look at this additive. And what we see is that these samples do have an additive. So there's a change in the spectra based on the additive that is added. So if we go back to our PCA plot, What we can do here is we might decide, well, we don't want these because they're outliers in this case, so we can mark them. You just click on them here. And what is nice about the unscrambler is when you mark them in one, it marks them in your other plots as well. So you can see where things fall. If we right-click, we can recalculate without marked. Okay. And now we see we have a pretty good model here. And again, you want to make sure that your loadings make sense. So PC1, it looks like a spectrum. If we increase the principal components, that still looks like a spectrum. And at some point, it starts looking like noise. A little trick, if you want to look at more than one loading at a time, you go up in this area and you just type the number of loadings. So you can see how they are on top of each other as well, how each individual one contributes. So if we want to look at your sample grouping here, we had these octane levels. And what we see is a clear pattern based on octane level through PC1 and PC2. So your low levels of octane have not as strong a peak here, and the high has a strong peak here. And that's how you interpret that. So, how to be a good data analyst. So first, we have our multivariate analysis workflow. The first step is you're going to collect your data. That's your sampling, your acquisition. You might have historical data that you're going to look at. First thing you want to do is check the data. Always plot it, visualize it, make sure there's nothing egregiously wrong with your data. If you have a super noisy spectrum, for example, or someone made a typo in a number, you might see it there and be able to correct it before you try to make a model. Then you're going to build your model. You want to check that model, interpret it, make sure that it makes sense, determine how many principal components you want to use. Then you apply your model to new samples. Let me show you how we do that on this octane data. So once we have this model built, what we can do is go back to our original data, task, predict, projection, and now I'm going to do my test set, and we're going to do NIR spectra. We're going to use PC1. Now what we'll see here is the green data points are the projected values, the new data, and the blue are your calibration set. And what you see is there's 4 out here that are outliers. So you might want to take a look at those, and we mark them. If we right-click in here, we can view numerical, so you can see which data points those are. So it looks like it's the last 4 samples. If we go back to our data set here, we see the last 4 samples had the additive in there. So you're able to interpret when you have new samples if they are part of your original, are they similar to your original data set or are they different? And you can see in your influence plot here that they're very far out here. Those are the same ones. So you apply your model to new samples to test it, to check your results, to make sure that your model makes sense and it works with new data, because ideally that's what you want to use it for. So these are some tools to do this. You might have a design of experiments so that you make sure you collect the data and it's over the range that you care about and covers the variance that you care. When you check the data, you're looking at your statistics. You build a PCA model. That's when you calibrate and make sure that you have a good model to start with. You check that model using validation, some known samples so that you can check to make sure that your data is falling where you expect it to. And then when you apply it to new samples, you've got your prediction, and you can be confident at this point that your model is valid and that your results that come out will tell you new information about your new samples. So some basic rules. Make sure to use representative calibration and validation data. You want to make sure you have enough evenly distributed samples spanning all of the major variations that you expect. You want to select an appropriate validation method. Ideally, this would be a test set, so you can split into training and test. So you have some data with known values that you train it on, and then some data with known values that were not used to build your model, but you know what the known value is, and you can test the model that you build. Look for your outliers. Outliers are not necessarily bad. Sometimes they just carry interesting information. So you have to decide based on your application whether you want to keep them or remove them. But you do want to make sure that you are taking out your erroneous data. You need to select the correct number of principal components by studying the shape of your residual Y variance. Try to select your first local minimum. Don't use too many PCs compared to the size of the data set. That's when you start overfitting and you're describing noise, and your model won't be very robust. Interpret the patterns you see in the data by studying the scores plot. Make sure if there are clear separate subgroups, you may have to make new models for each individual subgroup depending on what you want your analysis to do. Interpret your variable relationships by studying the loading plot, but only on the models that you're satisfied with. You have to make sure that your models have been carefully worked through the 5 conditions above before you start interpreting these relationships. Don't transform or pre-process your data unless you know what you are doing and why. Make sure to use weights, 1 over standard deviation if the variables are of different kinds of data or have different ranges, like we saw in the McDonald's example. Check how well the model will perform when predicting new data by studying the validation results, and compare with your reference method. That's more for a regression model. Remember, practice makes perfect. It takes a long time to get good at this. So the more you work on it, the better you will get. And that is all. Let's see if we have any questions. Let's see. Is anti-correlation the same as negative correlation or just not correlate at all? Yes, anti-correlation would be the same as negative correlation. So basically what that means is as one variable increases, the other will decrease. That means that they are anti-correlated. Why can we not save the PC scores with the groups marked? I'm not sure what you're getting at with that, but maybe we can talk offline and try to figure that out. In the first example, how would I explain all the PCs? Right. So we're going to look at your loadings plot to explain the PCs. In PC1, we're just looking in this X direction. One way that you could look at that, you can plot 1 versus 1. So now you see this direction is going to be what is explained by PC1. And what we see is it's mostly being is your fat percentage and your energy, and a little bit of protein. PC2 then, we've got carbohydrates and protein opposite of each other. So it's an anti-correlation between protein and carbohydrates. So if something has a high carbohydrate and low protein, then it will have a high score on principal component number 2. 3 is only doing saturated fat. The 50% criteria, rule of thumb, are adjusted on the software. So no, it's just kind of a rule of thumb. This gives you a visual way. If it's explaining less than 50% of that particular component, it's not really involved in that component. It's very close to 0. So the vector, that PC vector, is not going into the carbohydrate or protein space. It's really going mostly into the saturated fat. Why is PC1 negative in explain variance? So the question is, why is PC1 negative in here, but it's showing, I think it was 42% here. So the PC1, these values are based on the calibration plot. So if we see our legend here, the blue one is the calibration. The red is actually the validation. So PC1 doesn't predict very well, but in the calibration, it does contribute 42%. It explains 42% of the data. Can we count on small values of 3 PCs like 10%? That's going to be dependent on your application. You're going to have to decide if you want to have that extra 10% of data explained. In some cases, you might add a PC that only adds 1 or 2% because it predicts better later. So that's sort of a judgment call when you make your cutoff. And what it is, you really look at this, you look for your local maximum. So here you would maybe say a PC4 model is the best, but I might stop at 3. Again, you want to look at your loadings and determine if it's explaining information that you're expecting. What happens when you do weighting mean centering for IR data? Good question. I will show you. If we do tasks, we can do weights here, and our spectra all update. Oops. Now if we plot our NIR spectra, it changes them completely. So the variation in IR spectra between each other, they're all on the same scale. That's why you don't want to mean center each individual variable in your data, in a spectral data. Now, if you wanted to reduce some of the variations, so you can see there's a little bit of scattering that's going on here and a little bit of baseline shift. So there's different types of pre-processing you can do. I might do a standard normal variate, and what that does is takes a mean across the spectrum and divides it by the standard deviation across the spectrum rather than each individual variable. Get back to the meeting. I have something that says the software automatically selects the optimal components. Sort of. It gives you a suggestion of what mathematically is considered the optimal components. You have to use your own judgment. Don't take anything for granted. The numbers will be right, but you need to decide if it actually makes sense. There are definitely some times where the software will suggest 6 factors, but with my knowledge, I can look at it and see that I only really need to use 2. And if you can use less principal components, it makes the model more parsimonious and easier to understand and more robust. Let's see what else we have. How does this compare to principal components regression? So principal components analysis is really a qualitative analysis. It gives you an idea of what your data looks like and what the space looks like. In this case, when we did our octane data and we saw that there was a trend on octane in the PC space, then you might decide to, okay, because I do see this trend, then I'm going to do a principal components regression, and then you can do a quantitative analysis. So that's the difference between PCR and PCA, is that PCR is a quantitative analysis, so you're predicting actual octane values, where a PCA will tell you a general idea. It's not going to give you your actual numerical values out. I have been asked if I can send around the training files. I will check and see if that's something that we can share, but you'll definitely have this presentation so you can go through it again and watch. I think that's all the questions that I have gotten. Oh, there is a demo, trial version of the software. It is at our website, www.camo.com, and you can download the newest software. We're at 10.3 right now. And that's also where you will find the webinar after it gets posted. Thank you everyone for joining, and I hope everyone got what they wanted out of this data. The demo is valid for 30 days, I believe, but we can work with you if you need longer than that. If you have any questions, feel free to email me. It's hbrooke, B-R-O-O-K-E, @camo.com. Hope everyone has a great day.